Okay, so hey everyone, today I'll be solving the physics IGCSE past papers for the periodic that we have coming up. So question 2 from paper 33 of October, November 2020. The weight of child A is 125 newtons. Calculate the mass of child A. Figure 2.1 shows two children sitting on a seesaw. Okay, the weight is W equals mg, right? So you have your weight, which is 125. You have the m, which is the mass, which is unknown, and you have g, which is a constant, as 10. So 10 m. In physics IGCSE, take m as 10. They'll say, and if you're doing the actual IGCSE exam, it'll tell you in the first page, take the gravitational acceleration to be 10. Okay. Now divide by 10 to get your mass. So 125 divided by 10 is 12.5. 12.5. That's our answer. Now, keep the SI unit of mass is kilograms, so our full answer is 12.5 kg. They said to include the units in our answers. Okay, so you get it's out of 3 marks. You get the first mark for saying W equals mg. You get the second mark for saying 12.5, and you get the third mark for saying kilograms. Okay. Figure 2.1 shows child A and child B sitting in positions which balance the seesaw horizontally. Using the information in figure 2.1, determine the distance x. For this one, we're gonna use the formula W1 times GG1 equals to W2 times GG2. Okay, so we'll take W1 and GG1 to be for the child A, so I'll say CA, and W2 and GG2 to be for child B, so CB. You can take W1 GG1 to be for child B and W2 GG2 to be for child A. It's your choosing. Okay, so أكيد you want to write, since the system is to make it horizontal, that means it's at equilibrium. At equilibrium, the moments cancel out, right? So you're gonna want to write clockwise moments equal to the anti-clockwise moment. Write that because they'll give you a point for the mark scheme. On the mark scheme, they need you to write moment clockwise equal to moment counterclockwise. So I just wrote it like that. I just wrote it like this, just to get rid of it, because I'm not actually doing the IG now. I wrote it like that, but don't write MCW equals MCCW. Write it as moment clockwise equals moment counterclockwise. Okay. So W1 GG1 equals W2 GG2. So we have the weight of child A and the weight of child B, so I'll just substitute them in. 125, and the distance between the pivot and the child A, which is what we want, is x. So 125x equals to 250 newtons. 250 times the distance between the pivot and child B is 0.5. Okay, so times 0.5. It's given up in the figure here. X is 0.5 meters. Okay. Now, 125x is equal to half of 250. Half of 250 is 125. So 125x equals to half of which is 125. Okay, so x equals to 1. Okay, for this one, you get points for saying the answer 1 meter. You get a point for saying 125x is equal to 250 times 0.5, and you get a point for saying the clockwise moment equal to the counterclockwise moment. Okay. B. The person in figure 2.2 is pushing a child on the swing. State the name of the force that acts against the motion. So the motion of the swing is this way. Now, what force opposes motion in the air? As you can see, this person is in the air. You can choose air resistance. Air resistance is the answer. You can also choose drag. No, air resistance is drag. So when they ask you state the name of the force that acts against the motion of the swing, is air resistance or drag. Okay, so for the second question, paper 33, May, June 2021, a girl and her brother sit on opposite sides of the seesaw as shown in figure 3.1. Calculate the girl's moment. Okay, to calculate a moment, it is a moment, let's say mg for moment of the girl is equal to the force of the girl that's acting on the girl times the perpendicular distance. Now, I would advise you and for example in the real IG and in the school written, write perpendicular distance as words. Don't write D then the symbol for perpendicular. Because they in the mark scheme they needed this formula for a mark. I didn't get the mark because I didn't write it. And they said perpendicular distance in words. They didn't say D then the symbol. So I would advise you writing perpendicular distance, but whatever. We're not at the exam yet, so we have time to practice. So the moment of the girl is equal to the weight of the girl, which is given. The force of the girl, they told us the force, 240 newtons. So 240 newtons times the perpendicular distance, which is 1.9. And they want us to show that it is close to 460 newton per meter, or newton meter, sorry. So we open the calculator, and 240 times 1.9 equals to 456. 456 newtons, which we can say, or you can say it like this. You can say 460 newton per newton meter. Or you can write down 400, the answer is 456, which is close to 460 newton per meter. It's fine. Or you can write down 456 and I think they'll accept it, so I'm not sure. Okay, the seesaw is balanced horizontally, so it's at equilibrium. That means the moments cancel out. Calculate the weight of the brother. So this is his weight. It's given to us as W. So the moment of the clockwise, the clockwise moments equal to the counterclockwise moment. And again, I told you they award the full mark for this. So always write it down. Okay, we found so we're gonna write the moment of the girl is equal to the moment of the brother. So then we found the moment of the girl, which was 456. Or let's write 250 times 1.9 because Cambridge are specific sometimes. So we'll rewrite 240 times 1.9 again. Is equal to the moment of the brother, which is 1.2 times W or 1.2 W. Okay, so 240 times 1.9, we got it to be 456 equals to 1.2 W. So W is equal to 456 divided by 1.2, which equals, let's do it on a calculator, 456 divided by 1.2, 380. So our weight of the brother is 380 newtons. Okay. Part B. The weight of the girl in figure 3.1 is 240 newtons. Calculate the mass. I did this before, but I'll repeat it again. W equals mg. They gave you the weight, which is 240, so 240. And g is 10, so 10m. Divide by 10. The zeros cancel out here. M is 24, and the SI unit of mass is kilograms, so 24 kilograms. Okay. Now, paper 33, May, June 2014. A meter rule balances when the 50 centimeter mark is directly above a pivot. State where the rule, where in the rule the center of mass is located. Now it says it's balanced when the 50 centimeter mark is above a pivot. Okay, so our center of that would mean our center of mass is at the 50 centimeter mark because that's that point where we establish equilibrium, where our forces are equal and we're balancing horizontally. Okay, so that's part A. Part B. Figure 3.1 shows an apple and the 0.40 weight placed on the rule so that the rule remains balanced at the 50 centimeter mark. The center of mass of the apple is 25 centimeters from the pivot, and the center of mass of the weight is 45 centimeters of the pivot. Calculate the weight of the apple. Okay. As always, write the clockwise moments equal to the counterclockwise moment. And then you're gonna wanna write the weight of the apple, so WA times the perpendicular distance between the pivot and the apple. So I'll just write d p a is equal to uh, the weight of this, so 0.40 times the distance between the pivots, so d pw. Actually, let's write it in pure like formula. We'll substitute in the number station. I didn't give a mark for this, but it's better to show you're working. So times the w, or say fw, the force of w, times the distance between the pivot and the weight. So okay, let me just fix that w. Okay, there we go. Now you substitute in your numbers. You don't know the weight of the apple, but you know the distance, which is 25 centimeters. We change it to 0.25 or 25 times 10 to the power of negative 2. Keep it that way. Just remember the conversion factor. That way, when you're converting mentally, you might make a mistake, but when you do it on a calculator, it won't. So just keep it times 10 to the power of negative 2 is equal to, um, where are we now? The weight, which is 0.40, times the distance, which is 45, times 10 to the power of negative 2. Okay, so 25 times 10 to the power of negative 2 will give you 0.25. 0.25, the weight times the weight of the apple, is equal to, I'll just check the value I got from the calculation, 0.18. So is this value here is equal to 0.18. Now divide to get WA, 0.18 divided by 0.25. So 0.18 divided by 0.25, which gives us 0.72 newtons. That's the correct answer. Okay. Double I, the mass of the apple. So again, I'm gonna skip this because you find the weight of the apple W equals mg and you substitute. I did it 3 times. The apple is not moved. The weight is removed from the rule. And the pivot is moved to the left until the rule balances as shown in figure 3.2. Explain why the arrangement of figure 3.2 balances. Now my answer, what I wrote here, is correct, but it's not as specific as they want in the mark scheme. Okay, for example, I said the moment of the apple is equal to the moment of the rule. Here in the mark scheme, it said moments of the apple and the rule cancel. So I'm not sure, honestly, if they would accept my answer. So that's why I wrote the correct answer and I didn't give myself any marks for this. And then my answer is correct, but it's not specific enough. So we'll take the marking scheme answer, which is this. This is the mark scheme's answer. Now, the moments of the rule and the apple cancel, because in equilibrium, again, you're going to have your moments cancel. The moment due to the weight of the apple cancels the moment due to the weight of the rule. Or, okay, yeah, that's correct. I didn't write the weight of the rule in the marking scheme, but it's correct as well. So this is the correct marking scheme answer. Here, I'll just add the moment due to the weight of the rule. There we go. Okay. The pivot in 3.2 is closer to the center of mass of the apple. Compare the rule. Okay, the weight of the rule is greater than the weight of the apple because when the masses are imbalanced, the center of mass or the center of gravity is gonna lean closer to the heavier object. So you could say that the weight of the rule is greater than the weight of the apple, and that's our correct answer. Okay, so for paper 42, May, June 2021, define the moment of a force. Now, don't take this definition. It's correct, but the way I wrote it's a bit weird because this is the way they want it. They want it in this one. Define the moment of a force about a point. This is what the correct answer is. They'll give you a mark for this one in the exam. So take the second definition, not the first one. Okay, whatever now. Part B. Figure 2.1 shows an object of negligible weight. The object is in equilibrium. The object is free to rotate about its pivot. B. Calculate the value of force F. Okay. So as always, write the counterclockwise moment equal to the clockwise moment. and then you'd apply the right hand rule. So the force F is the counterclockwise moment because it's apply the right hand rule, you'll see it's counterclockwise. So I'll say CCW. Doesn't matter. You're gonna put these two equal to each other anyway, and this one's clockwise. Okay. So F1 D1 is equal to F2 D2. Here there isn't W1 GG1 or W2 GG2. You don't concern yourself with that. So F1 D1, we don't know how much F1 is. We know the distance between F1 and the pivot. It's going to be 12. So 12 F1 is equal to 500 because the weight, this is the mass, this is the, then you apply W equals mg to get the weight, which is 500, and 20 centimeters. Here the perpendicular distance is 20, so times 20. Okay. Now you could do it as 0.12 and 500 times 0.20 to make it Newton dot meter, but you don't need to. It's fine because they're gonna cancel out anyway. So we're here now to have F1 equals to 10,000. Okay, then you divide and you're gonna get 833.33 repeating. So I'll just use it as the repeating notation. Here we go. 833.33 repeating. Take it as 833 newtons, and that's your answer. Okay. Part C. Describe an experiment involving vertical forces to show that there is no net moment on an object in equilibrium. You may draw a diagram. Okay. We're gonna use the one in the book, the ruler with the pivot and two forces. Basically, for this one, you're gonna need to look at the book. I didn't look at the book, and I have the thing memorized by because of how many times they asked it in the exams, and I think they asked it in a past paper here. They basically take it like this. Take it as this ruler, or take it as this ruler, whatever. But you're gonna draw forces instead. So a meter ruler with a pivot would be used. Right? This is our basic setup. Now two vertical forces would be applied. Denoted F1 and F2. Okay. They both have a perpendicular distance d. Now, if you calculate these moments, you have to show or indicate that you need to calculate the moments in the mark scheme. If the moment was to be calculated and then you'd write the formula, I didn't. I just skipped it. The moment of F1 would cancel the moment of F2, which would establish equilibrium, which balances out the meter stick, showing that there is zero net moment in equilibrium, and those are your 3 points. And that's the answer. Okay. This is for paper 42, October, November 2020. Define the moment of a force about a point. I explained this force times perpendicular distance around the point. Take it as this explanation. Don't take it as the other one. Okay. Part B, figure 2.1 shows a uniform rod of wood suspended from a pivot. Calculate the weight W of the rod. For this one, W equals mg. And then the weight is 0.08 kilograms. So 0.08 times 10, which is 0.18 newtons. Okay. The moment of W about the pivot. Okay, so F times the perpendicular distance. F is the force of W, not the letter F. So you're going to take 0.80 because it's the weight. The W is the weight. So 0.80 times the perpendicular distance, which is 0.25, which is 0.20 Newton per Newton meter. Okay. Now, the moment of F about the pivot. Again, the clockwise moment is equal to the counterclockwise moment. So, you know that the W was clockwise, or yeah, the moment was clockwise. So now for the force, you're gonna see if you apply the right hand rule on the force F, you're gonna see that it's counterclockwise. So these two are equal to each other. So the moment is 0.20 Newton per meter. And you get the point. Now you calculate the force F. So 0.20 is equal to the distance, the perpendicular distance was given to be 0.75. And just F is unknown. So F equals 0.20 divided by 0.75. Which is, if you do it on a calculator, should be 0.27. So 0.20 divided by 0.75 which is 0.26667. So round it up to 0.27 newtons. Okay. So now, the angle between the vertical and the rod has increased. State whether the force F needed to hold the stationary must be increased, decreased, or stay the same. Now, أكيد it can't stay the same. So that's straight out crossed. And now you know that the work or whatever they wanted the moment. The moment, let me explain to you. So the force F will increase. That's one point to identify if it will increase or decrease or stay the same, because the perpendicular distance between the rod and the vertical has decreased. So you want to compensate, right? You want to still balance out the angle decreased, so the distance decreased along with it, and you know that the moment is, for example, the moment is, let's just take it as 0.5, for example, as our distance times, let's say, a force of 20 newtons, right? Let's say this was halved, so half of 0.5 would be 0.25 times, uh now let's calculate. Actually, let me start off by calculating this. So zero point 0.5 times 20 is 10. So this is going to give you 10 newton per newton meter. Now you want to maintain this moment, you want to maintain 10 newton meter. So uh let's say here 10 newton meter, which 10 is equal to, again, this distance was halved, so 0.25. Let's denote the force as F. Then you multiply, you divide 0.25 on both sides. You're gonna get 10 divided by 0.25. F is 40. So you can see, if the one of these have, the other one is gonna double. So basically, if it decreases, the other one's gonna increase to compensate in order to maintain the moment. So that's what's basically explained here, and that's it. Now I might have overcomplicated it, but look at the marking scheme and it'll explain it more clearly. Okay. Paper 42, October, November 2019, which is the last one. State two conditions which must be true for an object to be in equilibrium. So clockwise moment equals to the counterclockwise moment or anti-clockwise moment, and the forces must cancel out each other. That's 2 points. Okay. Now, figure 2.1 shows a uniform meter rule PQ in equilibrium. The distance PQ is 100 centimeters, so 1 meter. The mass of the meter rule is 0.12 kilograms and its weight is W. On figure 2.1, draw and label an arrow to show the force W acting on PQ at the center of mass. So our center of mass is going to be here, right? This is our center of mass. I denoted it as G. You don't need to denote it, didn't ask you, but just denote it. And this is our arrow here going downwards at the center of mass. Now, R is the reaction force. For every action, there's an equal and opposite reaction. Newton's third law. You'll need this for later. But it always acts at the pivot point or at the point where they meet. Now, if it was sliding, if it was full, the reaction would be here, but it's not. It's around a certain pivot. So our reaction force or our normal reaction would be on the pivot point. So it's gonna be here. This is R. Okay. So that's part BI done. Now, by taking moments about the pivot, calculate F. Okay, so the clockwise moment is equal to the anti-clockwise moment. So the moment of P plus the moment of F is gonna be equal to the moment of W, right? So then you're gonna want to add these two up. You're gonna get 0.50 times 10 to the power of negative times 10 to the power of negative 2 plus F times 90 times 10 to the power of negative 2 is equal to the moments of the weight. So these two are just the moments. I just expanded. Now why did I put times 10 to the power of negative 2 for each of them? And it was given in centimeters. We want to change it to meters to get it as Newton per meter. It doesn't matter though, because in the end it will cancel out, but it's better to put it in meters. So 0.05 plus 0.9 F is equal to 0.48 after doing all these calculations. Okay, you take this to the other side. 0.9 F is equal to 0.43. F is equal to 0.43 divided by 0.9, which is 0.48. And you get your 4 marks. Okay, calculate R. Now I said by Newton's third law, for every reaction there's an equal and opposite reaction. So the weight's equal to the reaction, the normal reaction. So keep the downward force is equal to the upward force, the downward force being the weight, and the upward force being the reaction. So R also equals 1.2 newtons. I know you can calculate the weight. We calculated it here. This is our weight. So it's gonna be 1.2 newtons, and R is also gonna be 1.2 newtons. And those are the past papers needed for the periodic. Good luck, guys.